Yeah, students, as a part of studying the system response and the performance, we are in a topic of transient response of a networks, where you are having a combination of passive components like a series combination and a parallel combination, where the network is consisting of a resistor and an inductor, a resistor and a capacitor, and a resistor, inductor and a capacitor in a series and a parallel connection. So, what is the purpose of studying this transient response? The performance or the behavior of a circuit or a network is going to be studied with respect to changes in the voltage and the power that you are connecting. Whether the changes are abrupt or suddenly changing, then how my circuit is going to be responding can be studied. Now, why we need to study? Why we need to study is, basically when I go for the real world applications, there is a time management of a network or a circuit, or a time analysis. Second one is designing, filter designing, and also signal processing. So if I want to apply those, I need to study the time response of a system. Time response of a system. Now, how much time that the system is in a particular state before reaching to the steady state will be studied with respect to time, called the time response. Now, we are going to study the time response by deriving a growth and decay current of a RL network. In order to study this, we are taking a resistor and an inductor which are connected in series, and to this series RL network, a signal will be applied which is called the analog signal from a source through a switch S. When the switch is thrown to position A, then the inductor is allowed to charge through a resistor R, and inductor is charging towards the Vi of t, or charging towards the supply voltage. When the switch is thrown to point B or a position B, then the inductor is allowed to discharge. Now, discharging time or a discharging time period and a charging time period can be determined by deriving an expression. So, how to derive expression? Now, when the switch is thrown to a point A, applying a Kirchhoff voltage law, what your Kirchhoff voltage law says, the algebraic sum of the potential drops around a closed path is equivalent to 0. That means applied voltage, voltage drop across resistor, voltage drop across the inductor is simply equivalent to 0. That means whatever the signal that you are applying, or whatever the power that is given to the circuit, is simply dropped across the two components. That means the energy is neither created nor destroyed. It is simply transformed into another form like a voltage drop. Now, when I am doing that, or when I am applying a Kirchhoff voltage law, what the expression you are going to get is nothing but a Vi of t minus R into I of t minus L into di of t by dt. If I remodify this expression, it looks like a first order differential equation will be in the form of this. Now, the solution for this can be obtained by taking a integral factor. Now, what is the purpose of integral factor? The differential equation which is in a non-pattern form is going to be converted to a required pattern form, or which can be easily solved by taking a integrate factor. So, here the standard equation is a first order differential equation whose integral factor can be written as exponential power of integration of coefficient of y into dx is simply equivalent to e power px. So, writing that then by taking an integral factor, we find the solution called the standard solution for this differential equation, which is simply y into integral factor is equal integration of q into integral factor into dx plus c, where c is nothing but a constant of integration. If I do the analysis, if I do the simplification, I am going to arrive at an equation which is going to be I of t is equal Vi of t by R plus a C into e power minus R by L into T. R by L into T. Are you clear with me? Right? So, this is the equation which is going to define the growth of a RL network with the application of applied input voltage Vi of t. Now, where C is nothing but a constant of integration, that constant of integration can be obtained by substituting the boundary condition. So, what is the boundary condition? We are going to take the values of t from 0 to infinity. We will substitute that boundary at a t is equal to 0. So, at a t is equal to 0 seconds, I of t is equal to I of 0 is equal to 0 amperes. How this is? Let us see when I am talking about my circuit. Now, you are applying some source or analog signal from the source. So, Vi of t is going to be Vi of 0. The switch is thrown or the switch is closed. My switch is closed. Now the resistor. Now we need to check the behavior of inductor. What is the story of a behavior of an inductor? So I'll write here. You are very much clear that inductor is a reactive element whose reactance is given by XL, okay, denoted by XL, which is simply equivalent to omega L, where omega is nothing but angular frequency, L is nothing but inductance of a inductor. Omega is equal to 2 pi FL. You are very much clear that the 2 is constant, phi is constant, L is constant. So thus, XL is proportional to F. Now you know that F is equal to 1 by T. So XL is inversely proportional to time. That means if T is equal to 0 seconds, then what happens is XL is going to be infinity. If the device is having an infinite resistance, it acts as a open circuit element. So thus, the inductor is a device whose reactance is going to be infinite ohms. So thus, inductor acts as open circuit element. Acts as open circuit element. So that means your resistance is there, but inductor is not there. Now the circuit is open. You are very much clear that the charges or the current will not flow in an open circuit. So thus, at t is equal to 0, I of t is going to be I of 0, which is simply equivalent to 0 amperes. 0 amperes. So thus, you are substituting the boundary condition in this. So, I of t is equal to I of 0. I am substituting t is equal to 0. Is equal to Vi of t, that is Vi of 0 by R plus C into, you have e power minus RL by L into t. Into t is going to be 0. Now, something into 0 is going to be 0. E power minus 0 is going to be 1 by e power 0. E power 0 is going to be 1, so it is going to be 1. So thus, at I of 0 is going to be 0. So 0 is equal to, this is a note, 0 is equal to Vi of 0 by R plus C. So C is equal to minus Vi of 0 by R, or I can say as Vi of by T. Is it clear? Substituting the expression of C in the above equation where you are having a C. So that expression is I of t is equal Vi of t by R plus C into, so in the place of C, what you are having is Vi of 0, but we took a t is equal to 0, but I am not substituting t is equal to 0, that's why I am taking t. So Vi of t by R into e power minus R by L into t. Now if I simplify this expression, I of t is equal to Vi of t by R. If I take Vi of t by R common, it is 1 minus e power minus R by L into t. Now in this something is there, or in this expression you are taking a ratio of resistance to the inductance. So this ratio of resistance to the inductance is called as a tau. What is a tau? Tau is called as a time constant. What I mean to say time constant? It is the average time that is taken with the circuit to make its a charge. Okay, to make its charge 0.6363 times of its maximum value. Whatever the maximum means, whatever the time that is taken by the system to reach 0.6363 times of its maximum value, clear, or 63% of its maximum value, that time is called a time constant. If I assume initial charge as 1, the average time that is taken by the inductor to discharge its energy from 1 to 1 by e times, 1 to 1 by e times is called a time constant. Is it clear? Time constant. So my final expression is going to be I of t is equal to Vi of t by R into 1 minus e power this is not R by L, this is going to be L by R, so e power minus t by tau. This is my equation A, which represents the growth current of a RL network. What it says? It is exponential equation. So the charge is increasing exponentially, okay, in a inductor. That is called a charge is increasing, called as a growth. If charge is decreasing, it is called as a decay. Clear class?